this way. Right? If A and B are congruent, and this is the set of all integers congruent to A, well, if A and B are congruent, then this set here is just the same as this one. Right? So these two sets, infinite sets, are equal. And with the same logic, with the mod 3, you'll get this. Right? So that's true. All right. Well, if B of 2 is A of 2, and B of 3 is A of 3, this equals that. Right? So well formed. So tick that off. Whew. Okay. I'm running out of board. I'll try to do part B here in this space. Okay. Now, you now have to prove this F is bijective. Remember, bijective means a one-to-one mapping between the elements of G and the elements of H. So in a sense, you're translating this set into this set, one-to-one. But that's not enough. Remember, you also have to do this third part. You have to show that each corresponding element, here and here, map. So, okay. But let's concentrate on the one-to-one mapping, the bijective part. Now, bijective, remember, means two things. It means the mapping is injective and surjective. Right? Done that a lot already. Okay, so let's start with injective. How do you prove it's injective? Okay, a little bit of revision. You have two sets, and let's call... now, injective means that each element in the target set, the codomain, gets mapped to at most once. That's the definition of injective. Remember? Done this, I don't know, half a dozen times already, I guess. Okay, so it gets mapped to at most once. So in other words, once or not at all. That's injective. All right. So if two elements here map, so let's call that A and this B, these two elements of your set A, this is your set B, and so if it's not injective, so in other words, you've got a many-to-one, a two-to-one. So if it's not injective, so if not injective, then you can have A not equal to B such that f of A equals f of B. Okay? So here you have a two-to-one mapping. And if you have that, if you just have one of them between your two sets, then it's this mapping F here. Your F is not injective. All right. So to prove that it is that there are no 2-to-1 or more, many-to-one mappings, all we need to do is we assume f of A equals B, and then prove that A equals B. Okay? Because if A doesn't equal B, if A does not equal B, like here, you've got two separate points map to the same point, that's not injective. So if we can show that if f of A equals f of B, that A equals B, that's your proof that this mapping F is injective. All right, well, let's try to do that. Right, so let's take now. What is the F? It's of this form. We're mapping this into this. Right? So let's take two arbitrary. So if we take, say, f of 6 So in fact, we're choosing this to be the codomain, right? This one. I mean, it doesn't work. It doesn't matter if you. Well, okay. So f of B6. Okay, and if it's injective, what's inside here will be equal to that. So A mod 6 residue class A mod 6 will be the same as B mod 6. So how to prove that? Let's see. All right. So yeah, we're assuming these two are equal. These two values are equal, and we're trying to show that these 2 points here that map to these are in fact the same point. That's how you prove injective. All right. Now this is, well, it's this. Okay. So now we can rewrite this as a what's 2 a 3, and that'll be equal to B2 B3. Okay, so that means this is equal to that, right? So A of 2 equals B of 2 mod 2, and A of 3 mod 3. So this equals this. All right. All right. Now what? So if this is true, that means A and B are congruent, and therefore A minus B so 2 divides this, and similar logic here, 3 divides A minus B. Okay, and therefore now if 2 divides this and 3 divides it, therefore 6 divides it. Okay? So that implies 6 divides A minus B. So therefore A is congruent to B mod 6. Mod 6. Okay, and therefore A, the residue class, A of 6 is B of 6. And that's what we wanted to prove, right? So we've proved injective, like here, see? So f of something equals f of something else, and if you can get from that prove that the something equals the something else, like the something is something else. So from f of b to f of b equals these 2 things, then it's injective. So we've proved it's injective. Okay. So, all right. Running out of board. Okay. So we've only done half of this, right? We've proved that it's injective. Now, how about proving that it is surjective? Because you have to do both to prove that it's bijective. Okay, surjective. Can you remember a theorem saying that if you have 2 sets, in this case 2 groups, that are of the same size, then if that mapping between them, the F, if it is injective, therefore it's surjective. Remember that theorem, which was theorem 27? You can go back earlier lectures, and it's on page 76 of your textbook if you're using a textbook. Okay, so I'll just state that again. So if your 2 sets, in this case 2 groups, if they are of equal size, and if the mapping between them is injective, therefore it's surjective. And it works the other way as well. like if the sizes of the two sets, two groups, are equal, and that mapping is surjective, then it's injective. So in other words, if you have a mapping both ways, I mean, between two sets of equal size, two groups of equal size, then if you have one, you have the other. If it's injective, it's surjective. If it's surjective, it's injective. So if you have one, you have both. And if you have one, that means it's bijective, effectively. Okay? So now look, these two do have the same size, right? This, we were saying this a bit earlier. This is of size 6. It has 6, where? Here, you'll see it. It has 6 elements. This has 2 elements. This has 3 elements. Together they have 6. So the sizes are the same, and therefore theorem 27 applies. So if it's injective, we just prove that it is injective. Therefore it's surjective. And if it's both, therefore it's bijective. So we've proven B. Okay? We've proven. Now the last little bit. I really don't have space. I'll have to stop here, clean the board, and we'll do the last little bit, proving this part, so that each element maps in the table. Each element in the table maps. So we need to prove this part. Right? I'll stop there temporarily.